Hello all, last time we did graph presentations. We saw adjacency matrix and adjacency list. For all applications today, we will be using the adjacency list as it offers a more compact way of representing our graph. So what are we going to see today? Today we're going to go over connectivity and depth first search. So last time we saw how to save a graph. Now what can we do with it? So let's say that I have a small graph here, and it's just 5 nodes labeled A, B, C, D, E. Here are some edges. What can I do? So I can just go and explore one of them, right? I can just go and say I am going to explore in G node V, right? Great. So what do I have about V? The only thing I have about V is children, right? So I'm going to go here and I'm going to say that for all V, U edges, I can just jump and explore the next node. Is this enough? Are we done? So let's say that I start from A and I break ties by alphabetical order. From A, I will go to B. Yeah. And then when I'm at B, since this is an undirected graph, I can go back to A. And from A, I will go to B. And from B, I will go to A. But that's not making any progress. I need somehow to say, hey, you have visited A, you should not go back. So that is exactly what we're going to do. We are going to say that we are going to go explore only if U is not visited. And in order to make changes in U, we are going to update it when we enter explore. Okay, and just for future reference, I'm going to put here a pre-visit V and a post-visit. So this gives us our first application, which is the depth first search. So DFS for G, what we're going to do is first we're going to set everything, all the visited to false. And then we are going to start exploring only those that we have not visited yet. Okay? So here what will happen is that I'm going to start from A. I'm going to go to B. B is going to look back and see that A exists, but we're not going to take it. So from B, we're going to go to D. D is similarly going to say that B exists, but we're not going to take it. Instead, we're going to go to C. From C, we're going to see A. And we are not going to take it. And then we are going to, since there are no more children for C, we are going to go back to D. Then from D, we have one more child, E. Then Again, we are not going to take back to D because that's where we came from. Instead, we're going to return, return, return. Okay? So I can now redraw this graph. I can start from A, go to B, go to D, go to C, go to E. Okay? And these are the edges that I did follow from here. So these are here. Okay? And from D, I'm going to C, sorry. Okay, these are the black edges. Let's add with green the ones that we did not take. So from C to A, and we have also which am I missing? I think, oh, we have all of them. So we see that we have two kinds of edges. Here I'm going to represent the black edges as tree edges, and the green edges are going to be called back edges. Okay? Quick question. How many black edges do I expect? So every time I follow a black edge, I will mark one more node as visited, and I have an entry point. Therefore, I cannot have more than n-1 tree edges. And in connected graphs, there are exactly n-1 tree edges. Let's do our first application. So this application is going to be graph connectivity. Given a graph, return if it is connected. So what we're going to do is something very similar to our DFS, where again we are going to mark everything as not visited. Then we are going to explore from a single node. And if it is connected, it should visit all of the nodes. If all of them have been visited, then the graph is connected and we can return true. Complexity. How long does this take? So we have O of n here, we have O of n here, and a single call to explore. If we go to explore, we can see that it does O of 1, O of 1, and here we can see that this is going to be the sum of the degree of V. Yes? Because every time it can go into every node once, and inside it will explore all the edges. But this is going to be 2 times E, which is O of E. So in total, our complexity is going to be linear. It's going to be O of V plus E. This is the best we can hope for, because we might need to always read the input. Next, we are going to talk about types of edges in directed graphs. So here, if I first want to define something else. I want to define my pre-visit to be open of V is going to be I, and then I is going to increase by 1. And my post-visit of V is going to be close equals I plus equals 1. So for every node, I'm going to track when did I open it and when did I close it, when did I start visiting it and when did I stop. Okay? Let's see. So we start with opening A. After that, we follow on with opening B. Then we open D. We open C for 4. Then we can't go to A, so we will close C, giving it a 5. Then D has no more children. It has a 6. Similarly, B has no children, so 7. And A has C that we have already looked at, 8. And E now is open and closed by itself, 9 and 10. Let's draw our tree again. So we have A, B, C, D, and let's put E on the side. So we have our forward edges being A, B, DC, not CD. Let's see the rest. So from C to A, that's going to be a back edge. But now we have more types. We have from A to C, and we have from E to D. Now, as we said before, these are going to be called three edges. These are going to be called back edges. And we have two new types. We have the blue ones that are going to be called forward, and yellow that are going to be called cross. How can we distinguish between these? So for each one, we are going to have edge UV. And when it is a tree edge, we will have open U is less than open V is less than close V is less than close U. Okay? So if I wanted to represent it with parentheses, how they open and close, it would look something like this. UVVU. On the other hand, in the back edges, we have the opposite. We have open V is less than open U is less than close U is less than close V. So notice that this is exactly the same, but V and U are opposite. Forward is similar in the sense that it is the same as tree. And in cross, we have that V opens first and closes, and then U opens and closes. Could the opposite of this happen? Could I have open U, close U, open V, close V? The answer is no, this cannot happen, because if I open U, then because of the UV edge, I will open V before I close it.